Hopefully by the end of the talk, we know what that means.
Yeah, so I'm going to be talking about, I guess, black box separations in the quantum regime, which is not obvious from the title, but hopefully will become obvious from the title. But, okay. So in general, one of the biggest questions in cryptography is what assumptions do we actually need in order to build cryptography? This is massive ongoing project with lots of partial results and no exactly known answers. But in general, one thing we do know is that everything in cryptography, the existence of essentially any cryptographic primitive other than like distinguishability obfuscation, implies the existence of one-way functions. And since one-way functions are broken, if p equals np, this means that the existence of any cryptographic primitive implies that p does not equal n. So at least we have some basic complexity result from the existence of essentially any cryptograph. And we can draw out the map a little bit of the hardness of various cryptographic primitives. You can see that pretty much all cryptographic primitives imply one-way functions, which are equivalent to pseudorandom generators and commitments. But there are some, and in general, the class of primitives that are symmetric key primitives that are similar to one-way functions in hardness is known as mini-crypt. We also have a class of primitives that you all should know, primitives that cannot be built from one-way functions, but all imply public key cryptography in general, or key exchange, and this is known as cryptomania. And the key thing that we know is that you cannot go from symmetric key primitives and use them to build public key primitives. That is, public key primitives are in some sense harder to build than symmetric key primitives. And they must require, therefore, stronger assumptions. This is kind of a nice picture. Okay, so the main focus of this talk is what about in the quantum regime? Quantum cryptography is cryptography where honest parties are allowed to be doing some quantum to distinguish it from post-quantum cryptography, where you have classical cryptographic algorithms that are secure against quantum parties. For quantum cryptography, we have quantum algorithms that are secure against quantum adversaries. May or may not have quantum computation. And we might wonder, where do quantum cryptographic primitives or quantum versions of these cryptographic primitives exist in this kind of, well-defined map that we know from mini-crypt and cryptomania and all these things. And in particular, we have, at the very least, we have that classical cryptography implies that p equals np. And so we would really like kind of that if quantum cryptography exists, that if any quantum cryptographic primitive exists, then we would also have some sort of quantum version of p does not equal np. Okay. So this is kind of the main focus of the talk is complexity implications of quantum cryptography. So before I actually get started, I'll give a quick primer on quantum complexity theory and define a few quantum complexity theory classes in line of P and NP, various other classical classes. So first of all is BQP. BQP is the class of languages that are decidable by efficient quantum computation. That is, language is BQP if for all inputs x, if there exists a quantum algorithm, which I'll note by this guy holding a quantum state. If there exists a quantum algorithm which on input x outputs 1 with probability greater or equal to 2/3 if it's in the language, and outputs 0 with probability greater or equal to 2/3 if it's not. But all quantum computation must be randomized, so in some sense this is inherently a random. This is the first most simple quantum complexity class. Next is QMA, which some people call the quantum analog of NP. And QMA refers to languages that are efficiently quantumly verifiable when given a quantum proof. So it's essentially the same thing as NP, where you have a prover and a verifier. And X is going to be in the language if the verifier accepts some witness, and not in the language if the verifier rejects every witness. But here the witnesses are going to be quantum states. And the verifier, instead of being a classical algorithm, is going to be a quantum. So it's essentially just NP, but with a quantum verifier, and the proofs are going to be.
So just like a simple question, like why is it called QMA? I mean, it's just like MA, but why is it like the right analog of NP?
Yeah, so I guess the thing is I mean, really it's the right analog of MA. The thing is in the quantum setting, since everything is randomized, MA is essentially the randomized version of NP, or the BPP version of NP. So QMA is like the BQP version of NP, which is also the BQP version. It's just because everything. So yeah, for those who know what MA is, it's essentially MA with a quantum verifier.
You can also consider the class where maybe the proof is classical and verify the proof.
So yeah, you could also consider the class where the proofs are forced to be quantum or forced to be classical, while the verifier will still be forced to be quantum. And this class is QCMA. And if you remember from the title of the talk, this is going to be the class that we're concerned about more than QMA, just because this is the class that we were able to deal with. But yeah, so essentially the same thing as QMA, but proofs are now classical.
Question?
Yeah.
So both for QCMA and QMA, you allow failure probability.
Yeah, you allow some failure probability.
It's on the complete side or it's on?
On both sides, yeah. So if X is in the language, then it accepts some witness with probability greater than or equal to 2/3. And if X is not in the language, then it rejects all witnesses with probability.
Although it is worth noting that you can amplify this out to be 1-.
So BQP, QMA, QCMA are like the most important analogs of the classical P versus NP collection. But there's going to be one more complexity class that I'm going to care about in this talk, and that is PP. PP has a classical description. It's the class of languages that are decidable by Turing machines, by randomized Turing machines, which accept exactly greater than half of the inputs, essentially. But for the purposes of this talk, or for the purposes of the quantum setting, we can describe PP in terms of something called post-BQP, which is an equivalent complexity class, shown by Aronson 04. And PP represents the class of a computation, efficient quantum computation, where the efficient quantum computer has the additional ability to do post-selection. And post-selection essentially just means that it's allowed to do conditional sampling. And for those who understand quantum a little bit more, it means that the algorithm is allowed to perform a measurement and choose the result of its measurement. A bit more formally, you can say that it's the class of efficient quantum computation, where your decider will produce two outputs, and what we guarantee is that X is in the language and only if the verifier or the algorithm produces 1 with probability greater or equal to 2/3, conditioned on the second bit. Okay. So we say that X is in the language, or we say that a language is in PP if there exists a quantum algorithm such that X is in the language. If X is in the language, then the algorithm has its first output being 1 with probability greater or equal to 2/3, conditioned on the second bit being 1. And if X is not in the language, then the algorithm outputs 0 with probability greater or equal to 2/3, conditioned on the second bit.
So essentially, this is like, so I'm just thinking about the way this would work. So this quantum algorithm gets an instant, and then it runs something to try to decide whether it's in the language.
Yeah.
And the output is like a measurement of 2 qubits. And then if the last qubit is a 1, if the last qubit is 0, then we say like we don't know.
Essentially, if the last qubit is 0, you restart the computation and you
Right.
keep on doing it until you hit 1.
Right. Sure.
And you can do this an exponential number of times and still.
Okay, could you give us some intuition of like the additional power that this gives you over just BQP?
Yes. So it turns out that the entire polynomial hierarchy is in P to the PP. So this gives you like quite a lot of additional power. It gives you essentially the entire polynomial hierarchy of power. And there are a whole bunch of other things you can do. You can do essentially And the big thing you can do is that you can do conditional sampling.
Is there a restriction about being, expected polynomial, like expected polynomial number of restarts? Or can you just keep going as long as?
Well, it has to have probability greater than 0 of outputting 1, but as long as the probability is greater than 0, we'll just keep on doing it.
Okay, so like you can essentially do something like, hey, like I want to find like an independent set in this graph. And then like just sample a random independent set. And you'd be like, oh, is this an independent set? Like if it is, then the last bit. Yeah.
Exactly.
Essentially, it's how popular science portrays quantum physics. Over all possible solutions, select the one that's correct.
Okay. Well, that makes sense.
That's a great illustration. I'm going to steal that.
Let me check. Does EXP a subset of PP?
No, PP is contained in P space.
I mean, exponential time.
Yeah, PP is contained in P space. I mean, yeah.
But for example, I can run an algorithm where if I found the correct, it's what Justin suggests, I just like brute force search the entire space. If I find the correct witness, I mark the final bit to be 1.
Yeah, that's in P space. So
Yeah.
because to check whether, so you uniform over the entire space, you look at like one potential witness, but you need to be able to look at this witness in polynomial time to decide whether it's the thing in polynomial space. In X, we could take exponential time to even decide whether this is correct.
So PP is between exponential time and P space.
It's
No,
smaller
it's smaller
than
than
P
P space.
space, and P space is contained in exponential time.
But how? But even that with PP, I can just like search the entire exponentially large space.
You can search an exponentially large space, but you can only look at like polynomial sized witnesses. You can only, all witnesses have to be verifiable.
Sure. But I can, as long as the witness is short, it's polynomially large, I can still search the entire space.
Yeah, I mean, NP is contained in PP. So you can find any NP witness with it. So, let's go back to this question. We want quantum cryptography cannot exist if we have some quantum version of P equals NP. And so the right thing that we would want to say is that, hey, quantum cryptography cannot exist if BQP equals QMA. Slightly worse if BQP equals QCMA. Maybe one of these things will say that yeah, QMA oracle or QCMA oracle will be able to break all quantum cryptography. Yes, this is the hope. It turns out that it's not true. In particular, 1983, 1984, Wisner and BQP discovered that key exchange with quantum communication can actually exist unconditionally. So there's some cryptography that you can do if you allow quantum computers that normally would be in cryptomania, is much stronger than one-way functions in classical setting, but in the quantum setting, you can just do it. You don't need to make any assumptions, it just works. So maybe we want to then, restrict our view to only quantum cryptography that must be, cannot exist information. You can, look at quantum cryptographic protocols that are broken information. And even then, it's not true. These imply BQP does not equal QMA. In particular, Kretschmer in 21 and Stolp in 23 showed that pseudorandom states, which are a quantum analog of pseudorandom generators, they can exist even if BQP equals. In particular, it finds an oracle such that BQP equals QMA relative to the oracle, but pseudorandom states exist, and a whole bunch of other quantum cryptographic commitments and MPC all exist, even if BQP. It seems unlikely that quantum cryptography implies this complexity assumption that BQP does not exist. So we might ask, okay, well, BQP equals QMA is wrong, so what assumptions do we need for quantum cryptography? And if we go through the literature, we can see that most quantum cryptography fits into kind of three major categories, and I'll go through these. So first category is what I like to call quantumania. This is quantum cryptography, which does indeed imply that BQP does not equal QCMA. So all of post-quantum cryptography falls in this category. Post-quantum one-way functions can be broken by NP oracle, and so therefore also broken by QCMA oracle. But it also includes some more quantum primitives, such as certified deletion for a number of cryptographic primitives, as well as something which I like to call efficiently verifiable one-way puzzles. But this is essentially a variant of quantum computable. Everything in quantumania implies this quantum computable one-way functions, and everything in quantumania can be broken by a QCMA. Next is CountCrypt, which is smaller class. So before this work, at least, there are only 3 primitives that I would say very naturally fit in it. But this is the category of quantum cryptography, which is broken by a PP oracle. So by a post-BQP algorithm, you can break these cryptographic primitives. The top of these is pseudorandom states, which, as I said before, is a quantum version of pseudorandomness. There's also one-way state generators, which is a quantum version of one-wayness or a quantum version of one-way functions, quantum output, as well as one-way puzzles, which is in some sense the minimal primitive for this setting. And it's essentially a kind of minimal form of classical communication one-wayness. I'm not going to get too much into the details of the definition, but there are a number of primitives that fall into this CountCrypt header. And the key thing about these is that all of them can be broken by BQP. And finally, there is NanoCrypt, which includes the list of quantum cryptographic primitives for which we don't really know any complexity implications. And in this class, the most important primitive is this thing called EFI, which is kind of a minimal notion of quantum pseudorandomness. But the key thing to know about EFI is it's kind of a minimal primitive, and it is equivalent to a whole bunch of other things. Quantum commitments of quantum computation, as well as multi-party computation with quantum.
Q commitment, what we want to commit is a classical.
Yeah, classical bit, but also quantum states are equivalent as well. So either classical or quantum equivalent.
Why does classical imply something? Or
it's the whole paper to
okay.
what it does. So these are the 3 main categories. There's quantumania, which is primitives that are broken by QCMA, CountCrypt, which is primitives that are broken by PP, but not by QCMA, and NanoCrypt, which have no known classical complexity implications.
So why count the name?
Because PP is a kind of counting class. It's like essentially this moral equivalent to sharp P, which is, where you can count the number of accepting computations. But yeah, I guess from the perspective post BQP, it doesn't make sense, but in general, PP is considered a count.
It's essentially.
So to visualize these together, we can kind of stack them all on top of each other. And we can see that, most primitives in quantumania imply pseudorandom states and everything below them. Similarly, most primitives in CountCrypt or one-way puzzles, in fact, imply most primitives in NanoCrypt. So most of the time, you can actually go down the ladder and build the smaller world from the higher one. It's not 100% of the time. And also another thing to note about these worlds is that each of them has a kind of minimal primitive. So quantumania, everything in quantumania implies these efficiently verifiable puzzles. Everything in CountCrypt implies one-way puzzles, and everything in NanoCrypt implies EFI quantum commitments and quantum. But the most important thing that I think about these worlds is that you can't go back up. In particular, there is a black box separation showing that you can't build EV one-way puzzles from states, and people pseudorandom states can exist, even if BQP QMA. And there's some preliminary evidence showing that you can't go from anything in NanoCrypt to one-wayness. It's kind of one query. I'll put details you can see on the YouTube separation.
What's LMW?
It's the Lombardi right. So
Double check, the red cross is just a black box separation.
black box separation.
And the question mark is
It's just a weak black box separation.
weak.
It's not a full black box separation, it's like a one query.
Okay.
separation. So yeah, this is the key point is that you can't go back up, you can't go from NanoCrypt to CountCrypt to Quantumania. This is a reasonably well explored space. But you know, we might ask, okay, is this a complete picture? Does this capture kind of all cryptographic or quantum cryptographic primitives that people study? And the answer is no. There are actually a bunch of things that we don't really know where to put on this map. It's unclear whether they're broken by QCMA or PP, and nobody's really thought about it. In particular, I'm going to talk about 4 examples, or in this fork, we consider 4 examples. We consider classical communication key exchange. This is key exchange protocol, where both parties are quantum, but they can only communicate using classical messages. This is the so-called QCCC setting, quantum communication with classical, or quantum computation with classical communication. We also consider QCCC commitments, 2-round key exchange with quantum communication, as well as quantum money. I'll talk a bit more about, in particular, I'll talk a bit more about QCCC key exchange, and not, this is the wrong dot, it should be quantum money. I'll talk a little bit more about QCCC key exchange and quantum money. The other ones, you can just know that they're so important primitives. But the key thing to note is that we don't know where in these worlds that any of these primitives. There's a whole bunch more that we also don't know how to place that we just don't. But the key question of this work is, in what world do QCCC key exchange, QCCC commitments, 2-round QKD, which is key distribution, and quantum money belong? Can they exist if BQP equals QCMA? Can they exist if BQP equals PP? We will find out. So what is a QCCC key exchange? As I said before, it's the key exchange protocol where 2 quantum parties, file and quab, will communicate using classical messages. So at the end of a QCCC key exchange protocol, Qualis and Quab will agree on some bit B. Qualis and Quab are quantum, their messages are classical, and it should be the case that for any quantum queeve, queeve should not be able to tell what is the bit B just by looking at the transcript. So that's what QCCC key exchange is. Should be fairly familiar. What's known about it? Well, first of all, we know that you cannot build QCCC key exchange from EFI pairs. It's hard to build this from some nanocrypt. That doesn't mean it's a line nanocrypt. It's some sort of evidence of that. And we also know that you can't build at least perfectly correct QCCC key exchange from post-quantum one-way functions. So this is maybe some evidence that it doesn't even rely on mini-crypt, that it's actually cryptomania or very, very high up, since we can't even build it from one-way functions. And we also know that at the very least, this can't exist statistically. You know, an inefficient attacker can break any QCCC key exchange. It's not like quantum key, where it can't exist unconditionally. Okay, but in general, we don't know any sort of complexity implications of QCCC key. We don't know whether its existence implies any sort of complexity implications. We don't know whether it lies in nanocrypt or CountCrypt, or whether it lies in completely open.
Just to double check, no statistical security is proven.
I don't know if it appears in the literature anywhere, but it's like trivial. It's just because the transcript has to commit to the shared bit. Otherwise, there's no way that quality is
Okay. Because as far as I know, I actually one of my previous work studied but we prove like conditional result.
You prove the conditional result.
Yeah, essentially it is we make a mathematical conjecture. If that mathematical conjecture is correct, then it cannot be statistical security. But without that conjecture, we don't.
Classical key exchange? I mean, I don't think it matters, right? It should be the statistical proof that you're talking about should work both quantum and the classical case. Like in both this QCCC and the classical.
Why?
I don't know. I mean, well, I guess what he's talking about, at least I don't actually know what argument, but what Eli's talking about seems like it does not depend on qualis and qual.
Yeah, I mean, yeah, any transcript where two parties agree on a bit at the end of the transcript, at the end of the classical transcript, should commit to the underlying.
Yeah, I mean,
Because from Qualis's view,
I got it. Yeah, because there is no this is in the plain model now or random. Yeah,
Yeah.
Yes,
it's a plain. Okay. The next primitive that I'll talk a little bit about, just for motivational purposes, is quantum money. There's some variant of quantum money. I guess this is actually a mini scheme. But in the paper, we actually built something stronger. It's quantum lightning. It's not that much for now. But the idea of quantum money is that a mint will produce money states, which is going to be, this dollar sign in cat notation, as well as a serial number sigma. And they will send this money state to whoever wants the money. The money state will essentially represent a dollar bill. And the whole idea of quantum money is that people should not be able to copy their money. They should not be able to take a money state, create two money states, and give them out to various people, such that we will all verify under the same serial number. This is an impossible thing to do in the classical setting. You can always copy classical data. But since quantum states can be unclonable, this could conceivably exist in the quantum setting.
this is secret key quantum money?
This is a mini scheme, so it's public key quantum money.
Who can verify? Oh, just
So yeah. So yeah, anyone with the serial number can verify state. But yeah, I mean, you can consider stronger notions or results also. But the key notion of security is that a quantum cleave who's given both the serial number and a quantum state should not be able to produce two new quantum states which both verify under the same serial. Okay. So cleave gets the serial number and can want to verify yourself, but you should not be able to clone the state regardless. So in that sense.
So it fails to be verified
Under the previous serial. I mean, the mint is just some algorithm. So whoever runs this algorithm can generate a serial number. In practice, you would have some like central authority holding.
Do you need something like secret key?
No. This is not actually quantumized. It's something known as a mini scheme, which is slightly weaker, but yeah, it's just that anybody who wants can generate a dollar bill as well as a serial number being like, hey, this is a valid dollar bill for this number. And then
The idea is that the bank will hold those serial.
Yeah.
Or you can sign them. That way you can check that, yes, this banknote was actually manufactured by the. It won't be. Yeah, it'll be take your word that it's worth actual.
maybe you want to start your own currency. That's not like you.
This is how you have to Joe.
For quantum money, the bank doesn't have secret.
So this, yeah, for many schemes, the bank does not have a secret.
Okay. So no one can generate two quantum states under the same.
As part of the definition, so that's another definition that you could consider. As part of this definition, the person who chooses a serial number could conceivably generate many states for the same serial number. But yeah, you could also consider the stronger definition where nobody can generate two states, which we actually consider. Go ahead. And what's known about quantum money? Well, it is known already actually that quantum money does imply one-way puzzles. That is, quantum money can be broken by a PP oracle. It cannot exist if BQP equals PP. In terms of overbounds, it's known that you can build quantum money from indistinguishability obfuscation plus functions. And you can also build it from like these non-abelian group action assumptions. But there's not much known about what can build it. But in general, it's not clear whether or not this is in CountCrypt or in quantum. It's not clear whether you can conceivably build one-way functions from this. It's not clear whether you can break this with the QCMA oracle. And so our result is essentially that we show that QCCC key exchange commitments to QPD and quantum money all lie in particular, all of these, including the one that was already known, can be used to build one-way puzzles. And we show a black box separation from efficiently verified puzzles. So we show an oracle relative to which these primitives exist, but BQP equals QCMA. In particular, for quantum money, we actually show a slightly stronger claim. We show an oracle relative to which BQP equals QMA, but quantum money exists. But this is morally not that. And so, to answer the question, in what world do these primitives belong? Well, can they exist BQP equals QCMA? Yes, they conceivably can. Can they exist at BQP equals PP? They can't. And this kind of means that maybe they can be built from some assumptions that are below one-way functions. And so what's kind of the takeaway from this result is that not just pseudorandom states, but there's actually a large class of interesting quantum cryptographic primitives, which can be broken by a PP oracle, but cannot be broken by a QCMA oracle, and therefore could conceivably be built by weaker assumptions than any, because all the assumptions we use can be broken by an NP oracle. And kind of a fun fact is that in this paper, we actually separate QCCC key exchange from post-quantum one-way functions. We show that you cannot build one-way functions from key exchange. This is the opposite of in the classical setting, where we know that you cannot build key exchange from one-way functions. So it's kind of an interesting flip that goes on. I'm not sure if it's actually too meaningful, but it's kind of cute and musical. Right, so now that I'm done with our results, let's dive a little bit into the techniques. Feel free to interrupt and ask questions at any time. I'm going to start with some background on how previously pseudorandom states were separated from BQP equals QCMA. In particular, Kretschmer in 21 showed an oracle relative to which pseudorandom states exist, but BQP equals QCMA. He actually showed QMA, but I'll show the QCMA version for simplicity. A pseudorandom state is essentially a quantum version of a pseudorandom generator. I don't know why I wrote fair here, not fair. But the algorithm, the pure X, will take in some input X and produce a quantum state, state X, such that many copies of state X could be indistinguishable from many copies of a true. And so he showed an oracle relative to which these pseudorandom states exist. But if you look at any QMA algorithm, there is or QCMA algorithm, there is a way to efficiently simulate the prover, which then implies that BQP equals QCMA. QCMA provers in this oracle model can be efficiently simulatable by making some more calls to do. So what is the oracle? The oracle is just this UK, which is a collection of random unitaries. What is a unitary? A unitary is just a quantum input, quantum output function, essentially. There's more details, but it doesn't matter too much for this talk. But the key idea is that given a collection of random unitaries, you can get a random state. There's a collection of random functions. You can get a random state by just applying a random one of these functions to all zeros. Okay, so you can easily build a pseudorandom state using a collection of random functions, a random quantum of random unitaries. What about showing that BQP equals QCMA? Well, the key idea is that quantum randomness in general is completely useless for any program that has classical input and classical. This is, a corollary of Levy's lemma and this idea of super concentration of our measure for those who know what that means. But the key takeaway from this observation is that any classical program that uses a quantum randomness is going to have the same behavior regardless of what randomness is chosen, essentially. Okay. So more formally, for any algorithm Z making oracle queries, making most n oracle queries to a collection of foreign unitaries with extremely high probability, more than 1 minus 2 to the negative, 1 minus e to the negative, over the choice of u, you get that for all inputs, V will behave exactly the same if you replace its oracle with a completely different random. That is the choice of the unitary that is given to V doesn't matter. And more visually, this means that if you have any verifier, classical input that makes oracle queries to UK, it behaves exactly the same on all inputs as a verifier that just samples the unitary itself. Okay. And in particular, you can replace any verifier with a verifier that does not make any oracle queries to its quantum oracle. And so, if you have a prover with access to a p-space oracle, the prover can then look at this verifier and find an accepting.
The middle one doesn't have oracle access.
Why is, sorry, you go first.
Yeah, then what is the purple U prime?
Yeah, so the purpose, so U prime is a random unitary that's sampled by the verifier itself.
Oh, fine.
Can the verifier actually sample the random unitary?
You can do with a T sign. Yeah, there is a way to efficiently do this. At least it's good enough.
Okay, and why does the prover have p-space oracle? Okay.
So we'll just add this as part of the, just give it a p-space. And in fact, we can also give the verifier itself access to the same p-space. It won't actually affect anything because p-space is low for it. So the intuition here is that if you have a verifier that has access to a random unitary, you can replace that random unitary by making the verifier sample itself. And if you have a verifier that doesn't query the random unitary, then with the p-space oracle, you can find an accepting.
Is there like some intuition of why, like, maybe the hard part seems to be to think about like why the p-space oracle doesn't help you distinguish like the pseudo-random state from a random state or something, or like, is that not the point?
So this is actually easy because essentially the pseudorandom state is indistinguishable from a random state information theoretically. So p-space oracle is not enough.
Yeah, it seems really random. It doesn't seem pseudo-random.
Yeah, it is actually. So pseudorandom states exist kind of statistically under these oracles, but pseudorandom states are like a quantum output thing. But if you only care about classical input, classical output things, then the p-space oracle can,
Like, sorry, I'm just trying to understand. Like, couldn't you say like a random oracle still exists in the p? I mean, maybe I'm just like not understanding.
So if you consider the oracle of a random oracle, of just a random oracle, then p is not going to be equal to relative to oracle. Even if you give a p-space oracle, you're not going to have p equals NP relative to the random oracle p-space oracle. Because the random oracle is going to set, actually there's a proof that says the probability 1 over random choice of random oracle, p does not equal.
Yes, something here is fundamentally different because the pseudo-random states are classical and they can't use this classic. They're quantum, so they can't use this classical oracle to like separate.
Yeah. So you can't use the quantum oracle to separate PNN because it's useless essentially. Classical input output.
Okay, some intuition.
Why are you giving this space for oracle access?
Because we want an oracle relative to which BQP equals QMA or QCMA. And so what does that mean? It means that we should really give both the prover and a verifier. I mean, it would be meaningful to not give the verifier oracle access to p-space, but we can give it oracle access to p-space for that reason.
Can UK prime be sample efficiently?
Yes, it can, at least for the purpose of the verifier, it can, this is essentially use something called the T-design, which is like a quantum version of a keywise independent hash function. Since the verifier is query bounded, we just sample a T-design for T larger than the number of queries. And this will act exactly the same as a random. In general, with the p-space oracle, given any algorithm that has access to p-space oracle. Yes, with the p-space oracle, you can find accepting inputs for quantum algorithms. This is in some sense because PP is contained in p-space.
So if UK prime can be sampled efficiently, then I'm confused why UK is a useful oracle to begin with.
It can be sampled
Let's say
efficiently internally, right?
yeah.
But
If even the lemma in the previous slide is false, let's say some
okay. So there's a key subtlety here, which is it's sampled efficiently because the verifier knows how many queries. So the UK it samples efficiently is going to fool just the number of queries that the verifier. But if you want to make a pseudorandom state, you don't know how many queries the adversary is. So you can't sample something that will efficiently fool all polynomials.
Oh, okay. So if the query number is unknown beforehand, then I need the oracle.
Yeah.
But can I say, because for the efficient verifier, I can always query polynomial times. So I can just find a large polynomial and sample by myself.
Yeah, so yeah, this efficient verifier, you know exactly how many queries it makes. So if you wanted to make a version of the verifier that samples its own unitary, you just need to make a unitary of the length that will exactly pull the number of queries this was. But this is essentially it. This is essentially the whole proof that shows that, hey, under this oracle, and as well as p-space oracle, BQP equals QCMA. And we want to show the exact same thing. We could do an example of QCCC key exchange.
Yeah, I'm sorry. I didn't follow. Why does it find? Why you show this?
Okay, so the reason this shows this is because we have given an efficient algorithm that finds an accepting proof for this verifier. This verifier acts exactly the same as all inputs as this verifier.
Which can produce pseudorandom state.
No, this is the QCMA verifier. So if this is a QCMA verifier, then we have an efficient algorithm that can produce proofs for this QCMA verifier. And so therefore we have an efficient algorithm. This whole thing is an efficient algorithm which decides the same language that this verifier. And so we have a BQP algorithm. This is a BQP algorithm to decide this QCMA.
The BQP algorithm with
Yeah, with p-space oracle. So what's Oracle? Our goal is to show an Oracle where QCCC key exchange exists, but BQP equals QCMA. And so therefore we want to show the QCCC key exchange exists when cloudless and cloud are both making Oracle queries to some Oracle O. But under the same Oracle O, any prover for a QCMA language can be simulated efficiently. And so what's the idea here? Well, we'll start by defining an ideal key exchange protocol. So let's say we have some random function f floating in the sky, such that only Alice and Bob have access to it. You know, kind of an imaginary scenario, but this is a scenario where we can easily build a key exchange protocol. In this dumb key exchange protocol, Alice will send her private input x to Bob. Bob will send his private input y to Alice. And then they'll both apply f to x and y. Since only they have access to f and x, y, you know, this is going to be the same value, so they'll agree. But any adversary query will not have access to f, and so we'll be unable to distinguish f of x, y. So really silly key exchange protocol, but it's secure if the adversaries don't have access. Right? And so the key idea behind our oracle is that we're going to lock away access to F. In particular, what we will do is we will give Alice and Bob, we'll define this thing keygen, which will sample a random X and produce X, as well as a key corresponding to X, which we'll call key X. And the key idea will be that the only way that you can query F on X and Y is if you have either the key for X or the key for Y. Okay, so we define this oracle mix, which takes in X, Y, and the key. And if the key is equal to the key for X, or the key is equal to the key for Y, then it will output F of X, Y, and otherwise it will just say, hey, failure. Okay, so we're locking away access to F underneath the key for X and the key for Y. And so our key exchange protocol then is that Alice will sample X and its corresponding key, Bob will sample Y and its corresponding key, then they'll both share X and Y to each other, and they'll both use mix to query F of X, Y. Both Alice and Bob will know what F of X, Y is, but they won't actually reveal F of X, Y, since any party listening to this protocol will not know the key for X or the key.
So this should be thought about like some sort of like conditional sampling in the sense that like the key, maybe like X is like a graph, and like maybe the key is like a big independent set in a graph or something. But, I mean, something that's hard for PP.
Yeah. Yeah, I mean, like if you wanted to consider, classical key exchange, you could think of like X as G to the R, and the key is just R or something like this. And this would give you Diffie Hellman.
Yeah.
Okay. So this protocol is entirely classical. So this actually is classical key exchange protocol. It's not going to have anything quantum in it. But there's an easy way that we can force Alice and Bob to both be quantum algorithms. Can anyone guess what we do to force Alice and Bob to be quantum?
The keys.
Yeah, we just make the keys quantum. Now Alice and Bob have to be quantum algorithms if they want to use this key exchange. Okay. So we created an oracle under which key exchange exists, but only if the parties are quantum. Okay. And what we want to do is we want to show that, hey, under the same oracle, you can't build classical key exchange. You can't build classical one-way functions. Okay. In particular, to make this oracle a little bit more formal, I said that the key for X is going to be the state X. What do I mean by this? Well, let's just say that the key for X is going to be some random unitary of X. And here the random unitary is going to be hidden up in the sky, but nobody is going to have access to it other than through state check. Just to make it a little bit more formal. And the final oracle we're going to add in is this p-space oracle, which is an oracle for any p-space complete language, just as in.
So is it hard to reverse this random unitary? Like if I see you that.
Yeah, you can't even query the for dimension. So you definitely can't query the
Well, you can query it on a random, and you can't choose it, right?
Yes.
Wait, then how is X?
X is random by state check.
No, how is X?
So I guess I'm not saying what it means to say that the state is equal to this. What you would actually do is essentially run the inverse of U on the state and check if it's equal to X or if it's equal to Y.
So you kind of have indirect access to you through mix as well, right?
Yeah.
Like only Alice and Bob have access to you.
Nobody has access to you directly. Alice and Bob, as well as all other parties, have access to you only through state gen and mix, which is this kind of limited access to you.
But then how do you do this?
How do you use inverse? So I mean, mix under the hood is using U inverse. It can be, at least that's one way to define it. But nobody can access U inverse.
So essentially, state gen gives you U of X for random X, and then mix, you can input a U of X and Y and check if U of X equals, or U of Y equals U of X. Okay.
No, but then you have to run straight in a lot of times, hoping that X comes.
Yeah, exactly. The key idea is that mix is useless. This state is useless unless you've already received it from state. So you can only essentially run udagger on states that you've already received directly from you. So it's kind of useless.
So it's not efficient. Right?
The key exchange protocol is efficient. So the key exchange protocol is just this thing, right?
No, but then Alice has to run mix.
Right, the mix is an oracle. She's running the oracle. The oracle is just one oracle. I mean, it is efficient. It's running you and then
Use like
sure, okay. Yes. Enough fun to know, but okay. So our final oracle is a piece-based oracle. And it turns out it's not that hard to show that this key exchange protocol is secure. It does require actually quite some work. But the intuition is there. It's secure for exactly the reasons you would expect. It's just that any party without querying StateGen itself is not going to be able to query it on accident.
Hold on, I think I missed something. So isn't that if, so if can see X and Y.
Yes,
So it can also run StateGen.
yes. But every time she runs StateGen, it's going to sample a new input. So she's never going to get the key for X or the key for Y. She's going to get keys for different values. She's going to get the key for Z.
StateGen doesn't allow you to
Yeah.
choose.
It chooses it for you.
it's really a randomized.
Yes. So then this is the easy part, showing that key exchange exists. The hard part is showing that BQP equals QCMA relative to this oracle. Note that we know from the exact same argument as Kretschmer that this oracle unit, that this U, is kind of useless for any classical communication primitives. And so we can kind of assume that this entire oracle StateGen is useless, and all these queries to the U inverse are useless. And really the only thing we need to worry about is whether f of x. Okay, so we need to show that for any QCMA verifier, any of the queries that it indirectly makes to f of xy will not be able to help it in deciding. And the key idea here is that we are only allowed to query f of xy at random points on the so you can only query f of xy on points that you've received from StateGen. Can't query it anywhere you want. And we'll then show that, hey, querying a random oracle at random points is not going to help you decide anything. In particular, what we'll do is we can consider a QCMA model where you have a verifier that makes random queries to some input, and you have a prover that can query F and not. And what we'll show is that this is exactly equivalent to a similar model where the verifier and prover have access to different oracles. That is, the prover, even an inefficient prover, should not be able to communicate anything about F to a verifier who only has random.
They'll never query the same.
Yeah.
Why does the verifier only have this fuzzy access? Like, why does it only have?
So this is, I guess, the intuition. It takes a little bit to show. It doesn't actually. There's a little bit more wiggle room, but it turns out that this argument enough.
Yeah, okay. Maybe you can sort of see.
I mean, yeah, it's because they can only query at some points given to them.
Yeah.
But once we show this is kind of enough to finish the claim, because we can then show that, hey, verifiers can actually sample the random F themselves. They don't need to rely on this oracle in the sky. And so therefore we can simulate the prover using a piece-based. Just the same as we did with the random. And I call this random function super concentration to match with our random super concentration, because it holds with extremely high probability over the thing. How does this work? Well, for those of you who have seen it before, this model where the prover has arbitrary oracle access to F, and they can send some short digest to the verifier there. This matches very closely with something that's known in the literature of cryptography as the auxiliary input random oracle. Note that we say a primitive is secure in the auxiliary input random oracle model if it's secure against adversaries that are given some arbitrarily computed short digest about the random. And how do people in general prove things about auxiliary input random oracles? Well, there's this thing called a bit fixing lemma or pre-sampling lemma that shows that anything that's secure anything that's secure in the auxiliary input random oracle model, only if it is secure in this thing called the bit fixing model, where the prover, instead of having arbitrary query access to F, can only fix some polynomial many points. So in particular, they'll choose some point of their choice. They'll set f of 0 equals 100, f of 2 equals 101, whatever it wants, and then send some digest to the verifier. But then the rest of f on everything other than those points will be freshly randomized. Okay, and it turns out that these two models are morally equal. What?
The bit fixing gives more power to them.
You
can often do better like that. There are other techniques other than bit fixing using which you can do better about the AI.
Yeah, this is true. This is true.
Bit fixing is like one technique.
Yes. That's right. If something is secure, but the important thing for us is that if something is secure in the bit fixing model, it is also secure in the game. Right? But yeah, you're absolutely right. It's not an if.
I guess the intuition here now is that the verifier is never going to query any of these fixed.
Yeah, the verifier is never going to query any of these fixed points. And so therefore, all of this stuff that the prover is doing is utterly useless, and it may as well just have query access to its own random. I'm going to skip the formal statement for time. But the key idea then is that we can use these kind of techniques to show that if we have any verifier that has query access to stage and mix, it's going to act exactly the same on all inputs as a verifier that samples its own U prime internal. And then it can, emulate stage and mix itself. Okay. In particular, this verifier has no query access. And so using p-space oracle, we can find an accepting. And so at the end of the day, we get that BQP to the O is also equal to QCMA to the O. And a bit more formally, we show that if you have some oracle parameterized by unit F, you'll stage n UF, var UF in p-space, and with probability 1 over the unitary and the random function. QCCC key exchange exists relative to O, and also BQP to the O equals QCMA. Okay, so this is how we show that QCCC key exchange does not imply efficiently verifiable puzzles. And this result generalizes to all these other primitives using fairly similar arguments. Okay. Note that for quantum money in particular, we again show the stronger separation that BQP actually is QMA, and this has to do with the fact that we don't need the random function for and turns out that the other directions of building the puzzles for these primitives is not that hard. So it's not that hard to show that these can all be broken by a BQP.
But was it shown in previous works?
It's not shown in previous works, but it's not
Like
that hard.
maybe folklore.
Yeah, it doesn't require that much. It's not it's not entirely true. I'm not going to present it here. Okay. So before I conclude, I want to talk about kind of a major issue of our separation. Maybe the biggest question is that our oracle is sampling a random X. It has some internal randomness. It's internally performing some measurements. And so for those who know quantum, this means that our oracle is a CPTP map, but it's not a unitary.
If that tells you anything.
All right.
Basically, this means CPTP maps are algorithms that can do randomness and do measurements and whatnot, but they can't do anything non-physical. They have to obey physical laws.
It can also be viewed as you have some auxiliary input and you apply the unitary and you drop the auxiliary.
Could you do something where you map, say, everything that's not the zero state onto the identity, and everything that is the zero state onto an EPR pair where you then perform the unitary on 1/2 the EPR? Because this should give you a superposition over X tensored with UX.
Yeah, I mean, you can definitely think about this. I have thought about this construction in particular, pretty much exactly. It's not trivial.
Okay, I had a feeling that there's a reason that.
But it's not trivial, but it doesn't mean it's wrong. It might be right. So it's not fundamental that our Oracle is a CPT map, PMAP. There's a unitary version you can consider, which Dustin just mentioned. It's just not clear whether it works.
I'll have to ask you later about some of the difficulties you found.
Yeah, I mean, I actually have bonus slides on the difficulties, so yeah.
Are you saying like the user has to send like a half of the EPR here to the?
No, so you send in a zero state, and if you send in a zero state, it does operations. If you send in anything other than a zero state, it acts as the identity. And on the zero state, it turns your zero state into an EPR pair, and then takes this EPR pair and does a unitary on the other half.
Yeah, so this thing. The map that sends 0 to the superposition of K. It's false. Okay, but yeah, for those who are not quantum, and to say what this means for the black box separations.
Non-quantum.
For classical listeners, what this means is that our separation means that we rule out any black box productions that use the underlying primitives in kind of like a straightforward way that uses it in the forward direction. But we don't rule out things that do more complicated quantum operations like purification or reversing the computation. Which is, it's still a useful separation, and I think it generalizes, but that's all. And I'll conclude with some open questions. So the first question is, can we get this to be done with unitary oracles? Which is the question from the previous slide. The next question is, 3 of our separations are only for BQP equals QCMA, but it's not exactly clear that you can't get the same separation for QMA. I think you probably can. Some difficulties. And the final question is, are there any other possible separations that you can get using this technique? I actually suspect that there's quite a number of various quantum primitives that can also exist even if BQP equals QCMA using very similar techniques. We did 4 primitives, so I don't know how many would be appropriate to. All right. Thank you.